Vanadium oxide regeneration review. This comprehensive review discusses the paper titled Oxidative Regeneration Study of Spent Vanadium Pentoxide Catalyst from Sulfuric Acid Manufacturer, which provides critical insights into designing next-generation vanadium-based catalysts with enhanced durability, regenerability, and catalytic stability. The work focuses on evaluating regeneration efficiency under controlled oxidative environments, specifically 5% oxygen-nitrogen versus air. Using a well-designed fixed-bed quartz reactor system, these findings contribute to both industrial process improvement and reaction engineering design principles for catalyst performance and sustainability. Vanadium-based catalysts, vanadium pentoxide with alkali promoters on silica, silicon dioxide, serve as the backbone of sulfur dioxide oxidation in the contact process for sulfuric acid production. Typically, these catalysts consist of 4 to 10% vanadium pentoxides combined with promoter compounds such as potassium, sodium, or cesium oxides/sulfates supported on silica. These alkali promoters, 15 to 20% potassium, 2 to 5% sodium, and/or 5 to 15% cesium, enhance catalytic activity and thermal stability by lowering the melting point of the vanadate phase and stabilizing the molten layer required for continuous redox cycling. Alkali promoters such as potassium sulfate and cesium sulfate stabilize the vanadyl sulfate pyrosulfate complexes, easing the vanadium 5 plus vanadium 4 plus redox cycling that transfers oxygen from O2 to SO2. The fundamental redox mechanism can be written as 2V5 plus SO2 gives 2V4 plus SO3, and then 2V4 plus 1 half O2 gives 2V5 plus. This redox loop is a coupled diffusion reaction process. The catalytic surface must provide balanced oxygen absorption, electron transfer, and desorption of SO3 to avoid rate-limiting steps. Therefore, optimizing oxygen partial pressure, catalyst surface energy, and temperature profiles are key to achieving maximum conversion efficiency without deactivating the active vanadium centers. The rate of SO2 oxidation follows a Langmuir-Hinshelwood type model. This rate law shows that the temperature and gas composition directly control surface coverage and oxygen transfer. High P subscript SO2 partial pressure of SO2 can cause surface poisoning by excessive SO2 absorption, while excessive oxygen can shift the equilibrium toward inactive crystalline phases. A practical implication is that the reactor design must maintain intermediate oxygen partial pressure and uniform temperature distribution to avoid mass transfer limitations. Over time, vanadium pentoxide catalysts deactivate through sintering, crystallization, and loss of alkali promoters. Prolonged exposure to hot acidic gases cause phase segregation in the vanadium alkali silica matrix, leading to decreased surface area and activity. This deactivation is a classic reaction engineering issue where thermodynamic stability competes with catalytic mobility. Alkali volatilization changes the molten vanadate composition, altering viscosity and diffusion rates within the catalyst layer. This results in non-uniform active sites and poor oxygen mobility. The regeneration process must therefore restore oxidation states V4 plus to V5 plus and reestablish a homogeneous molten phase without inducing crystalline vanadium dioxide or inactive oxides. From a catalytic development viewpoint, this points to the need for new formulations that use thermally stable promoters or core shell architectures to prevent alkali loss while maintaining vanadium accessibility. Spent catalysts are P-listed hazardous waste containing toxic vanadium compounds. Traditional recovery via acid leaching, oxidation, and precipitation can reclaim vanadium, but waste containing but does not restore catalytic functionality. Therefore, oxidative regeneration within the existing matrix is preferred. It avoids waste generation and lowers operational costs. The regeneration process doubles as a recycling pathway, turning waste into reusable high-value materials. This embodies circular economy principles within chemical manufacturing and aligns with sustainable process design strategies. The study's regeneration data indicate that moderate oxidation, 5% oxygen in an inert 95% nitrogen environment at 550 degrees Celsius for 1 hour, yields the highest catalytic recovery. In contrast, regeneration in air, 21% oxygen, leads to excessive oxidation and crystallization, trapping vanadium in low-activity phases. From a kinetic standpoint, an overly oxidizing environment accelerates the transition from amorphous to crystalline structures, reducing both surface area and oxygen diffusivity. Maintaining a mild oxidizing atmosphere ensures that reoxidation proceeds in a diffusion-controlled manner rather than triggering bulk crystallization. Controlled oxygen flux selectively reoxidizes vanadium 4+ to vanadium 5+ species without inducing irreversible phase transformations. This understanding informs the design of new catalyst systems with oxygen buffering supports or promoters such as dual-phase alkali titanate or cesium silica matrices, which can tolerate oxidative conditions while maintaining structural integrity. In oleum production, where sulfur dioxide is converted to sulfur trioxide, occurs under high temperatures and highly acidic gas conditions. Catalyst performance depends on maintaining a stable molten vanadate layer. A well-designed catalyst must distribute vanadium uniformly, prevent iron-silica interactions, and dissipate heat efficiently. Consequently, poor architecture, heat transfer, and bed packing are vital design parameters that help prevent local hotspots and gas maldistribution. High surface area silica supports are preferred due to their chemical inertness in sulfating environments and their ability to retain structural stability up to 500 degrees Celsius. The porous nature of silica enhances gas-solid contact and heat dispersion, ensuring uniform reaction kinetics and thermal management through the catalyst bed. The catalyst is typically prepared by impregnating a silica support, either diatomaceous or synthetic, with a precursor solution containing vanadium sources, such as the active component, such as ammonium metavanadate, NH4VO3, or vanadyl sulfate, VOSO4, which decompose upon calcination to form vanadium pentoxide. NH4VO3 releases NH3 and H2O, while VOSO4 evolves SO2, SO3, and O2, both routes yielding vanadium pentoxide as the active phase. Alkali metal promoters such as potassium sulfate, sodium sulfate, or cesium sulfate, which lower the melting point of the vanadate mixture to create a mobile molten catalytic phase active between 400 to 600 degrees Celsius, and then optional additives like potassium hydrosulfate or cesium hydrosulfate, which stabilize the molten pyrosulfate environment and facilitates the redox cycle. After impregnation, the catalyst is dried and calcined at 400 to 500 degrees Celsius in air, which decomposes precursor salts to vanadium pentoxide and forms mixed vanadium alkali sulfates and pyrosulfates. This process yields a porous, mechanically robust composite with uniformly distributed active sites. Uniform impregnation is essential to achieve consistent catalytic behavior, stable molten phase formation, and long catalyst lifetimes. Non-uniform loading, by contrast, can cause localized crystallization, hinder redox flexibility, and accelerate deactivation. Silica's chemical inertness and structural stability make it superior to supports such as titanium dioxide or zirconium dioxide, which tend to form sulfates or degrade under sulfur trioxide and sulfuric acid vapors. Silica remains stable even under cyclic heating and cooling, ensuring long-term durability of the catalytic bed. Its high porosity and surface area provide an ideal matrix for dispersing vanadium species, promoting efficient sulfur dioxide oxidation, minimizing mass transfer limitations, and evenly distributing the reaction heat through the bed. In this study, an integrated fixed-bed reactor system was built to allow the oxidative regeneration process for the spent catalyst samples and the catalytic activity evaluation process for the newly regenerated catalysts. The fixed-bed reactor system was constructed using high-purity quartz components to prevent contamination and withstand elevated temperatures. The reactor assembly consisted of two parallel quartz tubes enclosed within a programmable tube furnace. The reactor tube contained the catalyst bed, supported by a 4 mm thick quartz frit with an average porosity of 40 to 70 micrometers. This design ensured even gas distribution and mechanical stability during heating. The bypass tube, a secondary quartz tube positioned parallel to the reactor tube, doesn't contain a catalyst. Instead, it provides a way to divert or balance the gas flow when needed without disturbing the main reactor, allowing for independent control of gas flow and facilitated rapid switching between regeneration and activity testing without disturbing the furnace environment. Because sulfur dioxide oxidation is strongly exothermic, delta H is around -99 kilojoules per mole, the isothermal control is critical. The reactor follows a one-dimensional steady-state heat balance where K effective times d squared T over dz squared plus negative delta H times R subscript SO2 equals 0, where K effective represents the effective thermal conductivity of the catalyst bed, T is the local temperature along the reactor axis Z, and R subscript SO2 is the rate of sulfur dioxide oxidation in moles per gram per second. Proper control of heat flux prevents thermal runaway, maintains uniform reaction temperature, and ensures kinetic data accuracy. Reactor insulation and flow balancing are therefore essential in industrial designs. Future catalyst pellets may integrate thermally conductive additives like silica carbon or aluminum nitrate to improve internal heat transfer and prevent local overheating, thereby extending catalyst life. Having both tubes inside the same furnace ensures that temperature changes are uniform and switching between regeneration and testing modes is quick and precise. The uniform temperature profile achieved by the dual-tube furnace configuration minimizes thermal gradient, ensuring that the reaction kinetics rather than the temperature variations govern the observed regeneration behavior. The catalyst bed temperature was monitored using a K-type thermocouple positioned 3 mm from the catalyst zone, ensuring accurate thermal readings while avoiding direct contact with the catalyst. Spent vanadium pentoxide-based catalysts were first tried at 100 degrees Celsius for 1 hour under ambient conditions to eliminate residual sulfur dioxide, sulfur trioxide, and water that may interfere with the regeneration chemistry. Following drying, the samples were mechanically ground using a mixer mill to achieve a uniform particle size distribution of 100 to 150 micrometers. This size range was selected to balance mass transfer efficiency with minimal pressure drop in the fixed bed. Approximately 10 grams of the ground catalyst was then loaded into the quartz reactor tube, ensuring uniform packing and stable contact with the fritted support layer. The entire assembly was leak tested to verify gas-tight operation before initiating the regeneration procedure. The regeneration process was carried out in a controlled atmosphere to restore the oxidized catalytically active vanadium species while minimizing structural damage and crystallization. Initial heating. The catalyst bed was heated to 550 degrees Celsius at a constant heating rate of 20 Kelvin per minute under a nitrogen flow. The sample was held at this temperature for 30 minutes to stabilize the bed and remove physically absorbed species. Oxidative regeneration. After preheating a 1 liter per minute flow of oxygen-containing gas was introduced through the reactor for 1 hour. Different diluted oxygen streams, e.g., 5% oxygen in 95% nitrogen, 10% oxygen in 90% nitrogen, or air, were used to evaluate the effect of oxidation potential on catalyst recovery. The goal was to reoxidize vanadium species from a reduced state V4 plus V3 plus back to the catalytically active V5 plus state without inducing excessive crystallization, cooling, and storage. Upon completion, the catalyst bed was cooled to room temperature under a nitrogen purge to prevent recontamination or over-oxidation. The regenerated samples were then unloaded and sealed in airtight containers for further analysis. The two key analytical procedures were conducted on the regenerated catalysts. Catalytic activity testing. The restored samples were immediately subjected to sulfur dioxide oxidation activity tests under standard operating conditions. This step quantified the catalyst's ability to convert sulfur dioxide to sulfur trioxide, providing a direct measurement of the regeneration effectiveness. And temperature-programmed measurements. Temperature-programmed oxidation and reduction analyses were performed to characterize the redox behavior, phase stability, and oxygen mobility of the regenerated catalysts. The result profiles revealed the ease of vanadium redox transition, which correlates strongly with catalytic performance. This integrated fixed-bed system provided a robust platform for studying the relationship between regeneration, atmosphere, and catalyst reactivation. Results demonstrated that mild oxidation, 5% oxygen and 95% nitrogen, effectively restored catalytic activity while avoiding sintering and crystallization, in contrast to aggressive oxidation in air, which led to structural degradation and reduced surface area. The study's integrated fixed-bed system provides a reproducible and scalable framework for industrial catalyst regeneration. In reaction engineering practice, this can be implemented in continuous regeneration units or rotating beds to minimize downtime in sulfuric acid production. In catalytic development, the same principles guide next-generation designs focused on self-regenerating catalysts with dynamic redox control. Future research should combine computational fluid dynamics and kinetic modeling to predict temperature profiles, reaction fronts, and mass transfer limitations under varying oxygen environments. Integrating these insights with nanostructured support materials will enable the design of longer-lived, self-healing catalytic systems. In conclusion, this paper bridges the gap between reaction kinetics, catalyst structures, and process sustainability. Mild oxidative regeneration preserves catalytic structure and redox activity, while the air regeneration leads to irreversible degradation. From a reaction engineering and catalytic development standpoint, the findings underscore the importance of coupling kinetic modeling, structural control, and oxygen management in catalyst design for sustainable industrial processes.